few actually aspects of the so-called Andr-Oort conjecture. I shall not even give a precise statement of the, well, definitions underlying the statement, but let me present a similarity, the pattern in which this conjecture may be phrased, which maybe it has similarities with the statements we have already considered. So in the first place, we have now so-called Shimura varieties as ambient spaces. This replaces the abelian varieties or the multiplicative tori that we have considered in previous lectures. And in these varieties we have spatial subvarieties, which turn out to be also Shimura varieties. And here the spatial subvarieties of the abelian varieties are the translates of abelian subvarieties by torsion points. And here the same, we have the torsion, so-called torsion cosets. They are translates of algebraic subgroups by torsion points. And then finally we have spatial points, which are simply the spatial subvarieties of dimension 0. And here we have torsion points in both cases. So in this, with this setting, the Andr-Oort conjecture is stated, may be stated in the following shape. Let sigma be a set of spatial points in a Shimura variety. Then the Zariski closure. So these varieties are algebraic varieties. So the Zariski closure of sigma is a spatial subvariety. So this has an entirely similar shape of as the Manin-Mumford conjecture or the Lang's conjecture that we have considered. So let me give now, for making any examples, some very brief history of what has been proved and claimed in this direction. So this is, in the first place, is this trivial in dimension 1. And the first non-trivial result, so it was conjectured by Andr in his book on G functions. And he also refers in this book to an apparently unpublished assertion, also conjecture of Coleman, concerning the spatial case, the Shimura varieties, which arise as moduli space for principally polarized abelian varieties of dimension G. So Andr refers to this statement. In fact, this statement of Coleman, apparently unpublished, was the conjecture in the form stated by e-Oort a few years later. This is published in the proceedings of a conference held in Cortona. Also the CM the points of complex multiplication. So then Andr, I must say, also already in the book foresaw some similarity. He didn't state anything in definite form, but he spoke about the similarity of this conjecture with the Manning-Mumford and the others. And actually, he explicitly, in 2001, he gave a course with notes which may be found on his webpage. I don't think they have been published, but in these notes, he states a unified version of this conjecture and the Manning-Mumford, and which also has been done by Pink, I think. Okay, let us see some results. So Andr proved the conjecture for products of two modular curves. This is the only case that I shall illustrate, not in full detail, but later I shall speak more in more detail of this. And then this was, until recently, it was practically the only unconditional result in this direction. This was done in 1995, and about simultaneously, Edixhoven did the same, but actually he required for his argument the Riemann hypothesis for zeta function of imaginary quadratic fields. And this generalized Riemann hypothesis was present in all the subsequent proof until recently. So, yeah. Yeah. Exactly. Same Edixhoven then did the case of Hilbert modular surfaces. And then there are other intermediate results, but I only quote IA5, which did the general arbitrary case of curves. So he proved that if a curve in a Shimura variety contains an infinity of spatial points, then it is a spatial curve. So curves in an arbitrary Shimura variety.
I think Edixhoven also the product of any number of multiple curves in the geometry.
I see.
So just two. I mean, you get a conditional proof, but also one.
Yeah, I see. This I didn't know. So, and recently, so all of these methods were based, rather sophisticated variations of original Edixhoven principle. Recently, this was combined by methods based on Galois equidistribution, which had been worked also by Clausel, but by unifying these methods, recently Klinger, Ulmo, and IA5 So again, all of these are under GRH. And they claim the general case. Again, under GRH. So but recently Pila adopted the same principle that we have illustrated for the man in Mumford and for the problems of Masser. And he saw that these same principles could be applied to this context. And in a first paper, he reproved Andr's result. But more importantly, in a more recent paper, he proves quite a general case, which was completely out of reach of the previous method. Namely, he proves this statement for the varieties of the following shape. He takes first a product of n modular curves. And then he takes the product of this, so he mixes the man in Mumford and the e-Oort. He mixes, and here he can take two types of things, either an abelian variety or a product of any number of elliptic curves. Yes. Yeah, but there is something else here. There is something else, namely any power of gm to the n. I must say I don't know which detail prevents to do abelian variety times gm to the n. Anyway, this is, yeah. So this completely mixed case he claims only with the abelian piece product of elliptic curves. Okay, and yeah, this is, so I won't discuss, I will say only a few words on this general case, but I will now my yeah, so they may be described in two ways. So either, for instance, let us describe them when each of these modular curve is the affine line, in the simplest case. So a special subvariety. So first, a special subvariety of this kind of product is a product of special subvarieties of the factors. And so we already know what are the special subvarieties of the algebraic group factors. So let us assume for that each of the yi's is the affine line. Yes. So in this case, a special subvariety of, say, we are working over the complex, so of c to the n, this becomes c to the n, is, I may give this description, then it is much easier in words than in formulas, is a component, an irreducible component of a product of fibered products of modular curves. Over C times a product of vertical lines. So, for instance, for this fiber product, I mean the following. We take several modular equations. And we take the product of the curves. We take the curve defined by this relation and the component of this. So another way to describe the spatial varieties, which also is good for y1 times yn with arbitrary modular curves, is to go on the product of half planes and do the corresponding, do the relations for the tau values. I will this will come out in what I will say. In
Is it possible to handle also the case of quaternion algebra? So a quarter per half plane divided by something which is a compact proof?
this has not been. He has work in progress, but has not formally stated.
The passage to that is pretty straightforward. Just a density argument. Can I ask you a question concerning yesterday? Mass lower bound on the torsion is critically ingredient. That was effective, right?
Yes.
Well, yeah, of course, Peter is not effective because of
Yes, he uses also Siegel's. Yeah.
Siegel's analytic number.
Analytic number. So my plan today is to illustrate very briefly the proof by Andr of this case, and then compare it with the principles used by Pila applied in this simple situation. So let me, forgive me, I recall certain facts from the modular function, which perhaps are standard, but also I introduce some notation for the rest. So in fact, the simplest examples of Shimura varieties beyond points, I mean, are the given by modular curves. These curves parameterize elliptic curves plus additional structure, which may be, for instance, the choice of a point or subgroup of given order. And the simplest modular curve is the one parameterizing elliptic curves. And as a variety, its points, as a variety, it is simply A1, the affine line. It parameterizes just elliptic curves by means of the invariant. Let me recall this invariant. If we write an elliptic curve, a complex elliptic curve of Weierstrass form in this way, with coefficients a and b, then we may associate the invariant, which is defined as this constant multiplied 4 times a cube over 4 times a cube plus 27b squared, which is the negative of the discriminant of this polynomial, and so since this is an elliptic curve, it doesn't vanish. So two elliptic curves with the same invariant become isomorphic after an extension of the ground field. so over C. They become surely isomorphic. So this number is a point of A1, and it gives an elliptic curve up to isomorphism. So, and this elliptic curve from the analytic point of view, so algebraically it is defined by this equation, but it may be uniformized by, as a quotient, as a torus, as a complex torus, C over L tau. This L tau is a lattice in C, which is the lattice generated by 1 and by tau. And this tau may be chosen with in the upper half plane. And it is uniquely determined up to transformations in SL2Z. So this tau is a ratio of periods of the Weierstrass function associated to an elliptic curve. So we have an analytic map, this Weierstrass function and the derivative, which go to E. So, and this invariant J of E is actually the value of the modular, so-called modular function at tau, at the point tau. Let me recall this modular function admits a Fourier expansion, which begins in this way. Here Q is an abbreviation for e to the 2 pi I tau. And it is a function invariant under SL2Z. In fact, the tau is determined only up to this transformation. And it is actually, if it is actually a bijection of the upper half plane divided by SL2Z with C. Okay, then so we have this, so we may describe the elliptic curves also looking at this quotient, because this quotient gives uniquely the invariant. And we may, this quotient, for some purposes, it is useful to think as of a fundamental domain. It is a picture, I don't recall everything, but it is essentially this. Okay, then let us now say what are the special points in the affine line. So the special points correspond to elliptic curve having a big endomorphism ring. So the elliptic curve is a group, and there is an endomorphism ring which is always contains the multiplication by integers, always contains Z. But it can be in special cases larger. And when this happens, we say that the curve E has complex multiplication. And we say that the invariant associated to it is a special point of A1. So these special points, we can see if we look at this picture, we see that the endomorphisms are always represented by multiplications, and the terminology comes from this, by complex numbers. But these complex numbers have to preserve the lattice. And then these amounts, these forces tau to be quadratic imaginary. So these are the only possibilities. And the arithmetic of the values of j at this point is very interesting. There is a whole theory which I don't recall, but I will recall only a few things for later use. And the values of j tau in these cases, j of tau is algebraic and actually an algebraic integer. And last thing I recall now is that the degree of j tau over q is equal to the class number of the ring associated to the lattice L tau. What is this? This is an order. There is a ring of complex numbers which send the lattice into itself. And this ring is contained in the ring of integers of the quadratic field contained in tau. So tau lies in a certain q square root of d where d is square free and negative. And this ring has the shape z plus f times. So there is the ring of integers associated to tau, which associated to d, which I denote in this way, and this f is called the conductor. So this ring is contained in the ring of integers, and there is a class number, which is the degree of the value of j. So these facts were used in the first part of the proof by Andr. So let me so Andr wants to prove now. What does he want to prove? So let us do his result for the case when the Shimura variety is the plane. So we have a curve here, a plane curve. And we want to show that, now what are the special points here? Simply the pairs with the both coordinates corresponding to Cm values of invariants. So these are the special points. We want to prove that if there are infinitely many Cm pairs on the curve, this is supposed to be irreducible, then this curve is a special curve. What are the special curves inside here? They are the modular curves. What are the modular curves? So they are defined, these modular curves, for each n, one can define this modular curve called y naught of n. It is defined by a polynomial irreducible phi n xy equals 0. This defines y naught. This phi is rather complicated to write down, but the degree, the separate degrees, both in x and y of phi n, are the following. N times the product of 1 plus 1 over p for p running over the prime divisors of n. So this is approximately the reciprocal of the Euler functions. So, and these modular curves, they parameterize. So if a pair lies on the modular curve, This means that the elliptic curves with invariants x, so if x1, phi x1, x2 equals 0, says that the elliptic curves with invariants x1, x2 are related by a cyclic isogeny of degree n. So, and this in turn implies that if one of the curves has complex multiplication, then the other one also must have. So surely in these curves we find an infinity of points with complex multiplication, because we can prescribe arbitrarily the first coordinate and just solve the equation for the other. And but there are other exceptions, trivial or horizontal or vertical line. So we want to prove this. So the proof by Andr, so he tried to use the following fact of the modular curves. So if we look at the inverse image of the modular curve by the J function on both lines, we find that the inverse image is described by pairs tau 1, tau 2, where the second tau 2 is the value on the first tau 1 by a linear fractional transformation with coprime integer coefficients and determinant n. So we may describe the inverse image in this shape. Andr proved that f, let us exclude that it is vertical. So let us assume that there are an infinity special pairs. And I denote a general pair by x1, x2. So we suppose that this runs through an infinite sequence. So first of all, he took conjugates of x1 in order to make x1 large. And here he used a first arithmetical fact that the conjugates of the value of j run through all the, so one may take representatives for any prescribed ideal class. So he could, by conjugation, we may assume that x1 is the value of j.
So this is the principle.
Yes. Yes, this is thank you for the question. He first before doing this, he took the product of the conjugates of the curve over Q to make it irreducible. So we assume it is irreducible, but we don't know it is over Q. Then he took the product of conjugates over Q to assume that the curve is defined by rational coefficients. It is not anymore absolutely irreducible, perhaps, but it is irreducible over Q. So he worked with this. And then over some number field, yes, because we are assuming that there is a Zariski-Dense set of algebraic points, which are the CM pairs. So it is defined over the algebraic numbers, and then we can do this. So with this trick, we can take this value. This big D, this capital D, is the conductor squared times D, times small d, where small d is associated to the quadratic field of the first point. But now, what can we say about x2? Well, here I skip because of lack of time. He used the class field theory, essentially the arithmetical theory of the values of the j function, to show that, so we have a d1 and a d2 associated to x1 and x2. He first showed that for almost all elements of the infinite sequence, we can assume that the d is the same, so I put no index on it. And he could not show that the conductors are the same, but anyway, he showed that the ratio of the conductors associated to the 2 points belong to a fixed finite set. So this was preliminary and is done entirely with the arithmetic of the values of the J function. So by conjugation we assume this. So at least we have one large value because the logarithm of the absolute value of x1 by the Fourier expansion is asymptotic to pi times the square root of the absolute value of d. Now the second point, what happens to it? So the first tends to infinity. The second one could go to a finite point, which, however, we can move in a subsequence and assume that x2 converges to some y coordinate of a point at infinity on the curve. So the problem that he found was that it could converge to a finite point. Let us assume this, that this converges to C. Now, this convergence has to be rapid because we have a Poiseuille expansion of x2 in terms of x1. So the difference between x2 and C is, since we know it tends to 0, it must tend to 0 like a fixed negative power of x1 if we consider absolute values. So the logarithm of this is asymptotic to minus alpha times the logarithm of the logarithm of modulus of x1, which is in turn asymptotic to minus alpha pi square root of d1, sorry, because the conductor is still associated to.
Could you say again why one has this kind of convergence?
Because one considers a Poiseuille expansion of x2 in terms of x1. So since there is convergence to C, the first term is constant and then come negative powers. This alpha is, in fact, the first negative power is a rational number, but it is fixed. So there is this convergence. And now he looks at what happens under the inverse image by J. So he writes C will be some value of J at a point that we call zeta. And x2 will be the value of J at some point that we call W2. So by now the difference x2 minus C is essentially, the logarithm is essentially the logarithm of the difference between W2 and zeta, because the ramification index of J is bounded by 3 in the worst case. So we may say that also the difference W2 minus zeta behaves in the same way. Here we have a new number which I call kappa. So it is very small. We may also assume that W2 belongs to the fundamental domain, because the function is invariant by this. But now he uses, so you see these are values of the inverse function of J. Here we have an algebraic point because C is a point at infinity on the curve, so it must be algebraic. If we take the projective closure of the polynomial defined in the curve, it is given by an algebraic equation. And x2 is actually quadratic, no, is algebraic because it is a value. And actually now W2 will be algebraic of degree 2, quadratic imaginary. And of this we don't know, it will be probably transcendental by a result of Schneider. But in any case, now this behavior is like the theory, the transcendence theory gives lower bounds for these sorts of differences in much the same way that it gives lower bounds for the approximations to logarithms by means of algebraic numbers of bounded degree. And this was done by Masser. Masser already in 1975 gave a lower bound which showed that this thing, since W has bounded degree, this is crucial, is actually minus a logarithm of d1. So this is, oh, cubed, yes, sorry, and actually plus something. Yes. No, no, yeah. It is a deep result, and by means of this, so we have a contradiction, and so we know that both coordinates tend to infinity if we normalize the first by means of that conjugation. And now let us write the two coordinates, x1 and x2, as values of tau1 and tau2. And we can take them in the fundamental domain. And then tau1, we have already written this. It is not in the fundamental domain, but it becomes in the fundamental domain if we shift this by an integer. So the final value of tau1 will be of this shape, C1, I have already used the C, times F1 times square root of D1 over 2, where this C1 is 0 or 1. And tau2 will be of some shape like this. This is because we know that the conductor is exactly F2. So it becomes this, and the condition, because for this to be in the a condition for this to be on the fundamental domain is that A is at least the absolute value of B. So now let us take another Puiseux expansion, this time at infinity. And this shows that the logarithm of the absolute value of x2, since we now know that x2 in absolute value tends to infinity, we now know, so the dominant term in the Puiseux series will be some positive power of x1, and so will be of the shape, we have this asymptotic. Excuse me? Where beta is rational. Yes. And this gives by the Fourier, now we use the Fourier expansion for the J function, which was the main point. So we have f1 square root of d, of small d, asymptotic to beta times, so rho, I recall from the beginning that the quotient of the conductors belong to a finite set, so we may suppose on going through a subsequence that it is fixed, and it is this rho times the square root of d over A. And this oh yes, sorry. No, sorry. We can cancel the f's and simply here put the d1. Okay, and this now means that well, this is an asymptotic relation, but beta and rho are fixed, and a is an integer. So we may assume that a is fixed. And then, but the absolute value of b is bounded then, and going by a further subsequence, we may assume that it is fixed. And then we have, you see, these two relations combined give finally a relation of tau 2 in terms of tau 1, which is of this shape with fixed coefficients. So this
It doesn't generalize to more than
yeah, in fact, if one makes the assumption that they tend to infinity from the beginning, then it is very direct, and all the rest is doing.
class numbers. Why not?
Yeah. So now let me say something about Pila's proof. Pila also looks as in the methods that we have seen yesterday. He considers again the pair, so the uniformization going from the square of the half plane of the upper half plane to A2, and again considers the inverse image of our. So we have now a curve here, our plane curve, containing an infinity of spatial points, and we want to prove that it is a spatial curve. And we again consider the inverse image of x tilde. So now the spatial points, the inverse image of the spatial points will be no more rational points as it happened with the Manning-Mumford in the situation that we had yesterday. Now we only know that they are imaginary quadratic. But Pila developed, so he adapted his previous method to estimate rational points to the estimation of rational points of algebraic points of bounded degree, in terms of a parameter of a height bounded by a parameter t. So in place of the denominator, we have now a height, and any choice of height is equivalent. It does not matter which choice of height we do. And he proves the following result. So he proves this theorem. So let Z be a subset of some real space, which is definable. Here I will not, in a so-called O minimal structure over R. So this definable, this O minimal structure is simply a collection of subsets of all powers of R, and with certain axioms that are natural. I don't write them, but roughly speaking, we want that arbitrary set operations remain in the structure. We remain in the structure, and by product operations and also by projections. And we want there is an important axiom of finiteness for the boundary of the sets of the structure which lie on R, in R. And okay, this is somewhat technical. Yesterday I didn't even mention this because the sets with which we dealt with, I mean, he needed not to use this language and this theory. And now the point is that he has to apply these estimates to these sets which involve the J function. And this introduces a new difficulty. It was proved only until recently, I believe, by Peterzil and Starchenko. That the sets that we meet in this proof are definable in the minimal structure consisting, which is the structure which is generated, so to speak, by the subanalytic sets and by the graphs of the exponential function. So these the sets that are involved in this argument of Pila. And there is a reason for this, that we need to consider the J function in a non-compact, in the whole domain, whereas yesterday we needed only consider in a compact part. And since it has an essential singularity at infinity, it does not fall into the treatment which involves only subanalytic objects. So there is this additional difficulty. Anyway, the theorem was borrowed by these guys, and he could apply. So with this assumption, exactly. So the yeah. So he proved with this assumption on Z. So we let k be an integer and epsilon be positive. And then we denote by nk of a set, which is in our case this Z minus Z alg. So I mean the same as yesterday. So I must remove from Z the union of connected semi-algebraic subsets of positive dimension. So, and we count things here, but this nk is referred to the degree of the points, of the algebraic points that we want to estimate. This k is referred to the degree and is fixed, whereas t is the height, and we may take, for instance, the maximum of the absolute values of the conjugates and of a denominator, for instance. And so this is bounded by a number depending on z, on k, and on epsilon, but not on t, times t to the epsilon. So Pila applied this. Yes?
Generality probably, I mean, at least is as complicated as his work with Wilkie, right? I mean, he's using that, he reduces it to that, or he has to go?
No, he has to use this new tool provided by Peterzil Starchenko. Yes, plus that, yes.
I mean, this is any dimension?
Any, yes. Any dimension. So now we have one important ingredient, and the principle of the proof is like yesterday. So we take the curve here, we take the inverse image, we take the intersection. It suffices to work in a fundamental domain. So Z can be taken as the intersection of x tilde with f. Yes? K is the yes. Okay, and then we have a curve here defined by some equation. So this x tilde becomes simply the is defined by the equation, but calculated in the J. So it's simply this thing here, and he, by means of the results of Petersen-Starchenko, he can apply this theorem. So he can estimate. Again, he takes one spatial point and takes the conjugates. So these conjugates will give quadratic imaginary points on this lying on x tilde. And he can work, of course, inside the fundamental domain. Then the number of these points will be bounded by the height to the epsilon. And the height, however, may be bounded in our case, if we choose the point in the fundamental domain, it is easy that the height may be bounded by the absolute value of the of d1 plus d2, say, of the discriminants associated to the points, because they lie in the fundamental domain. So we have a bound for this to the epsilon. But now we know that the number of conjugates is equal to the class number of this, of the quadratic field of any of the largest of the two at least, and by the estimates of Siegel, the class number can be bounded below. Oh, really?
Any power.
I see. I see.
Then Siegel read his paper, and there's a funny story about that. I'll tell some other time.
Okay, so now we have the required contradiction. Yes, yes, and possibly inside the upper bound, it seems to be effective, but Pila thinks it is so, but so no, it is. Yeah. So, and the last thing I would say that well, my time is over, so I don't. There is some verification needed to show that in this case this set is empty. And it is not so difficult for curves, but it becomes the main difficulty in the paper of Pila dealing with the general case. And actually he does this by a new idea, namely he uses again the estimates for rational points inside the verification of this fact, because he finds that well, it's not. It's entirely different, and this part of classifying the algebraic part tends to become the heaviest in the developments of this. So, thank you very much.